Welcome back. Today we're going to talk about center of gravity. We're going to work from there. We're going to talk about centroids and center of mass as well. But let's talk about center of gravity. Center of gravity is the point where the weight force is applied. So as we've seen throughout the course, the location of a force is very important in both 2 and 3 dimensions to determine the amount of moment that that force can cause at various points or about various axes. So knowing where the weight force needs to be applied is important information. If you hear jingle bells over here, that's Lucy. We put a collar on her because we got tired of her hiding in the house and not knowing where she's at. So please ignore the jingles. The point where the weight force is applied, that's going to be the center of gravity. In this text, we use capital G to indicate the location. Now, if we have what we call a uniform object, that means that the center of mass is just going to be located at the center of gravity is just going to be located at the center of the object. Now let's figure out, how do we find, oh, Lucy, you're making all kinds of racket. Yeah, you. How do we find the location of said center of gravity? So let's say we've got a system here of some weights. So let's say I've got some weight out here. We'll call this weight number 3, and we'll call some weight here, some object with an amount of mass, weight number 2, and maybe some object right in here somewhere. We'll call this weight number 1. I don't know why I ordered them this way. And so let's say that this one is located at some x1, y1, and then it's going to be at some z1 location, right? And so this guy, we'll say he's out here at some x2, y2, and some z2 value. And then this guy's over here, right? You get the idea, right? We could label x3, y3, and z3 for that guy. But the point is, each one of these weights 1, 2, and 3, have an x, y, and z location. Now, let's say I wanted to find, let's say we wanted to find the y bar location Actually, let's not do that yet. Let's do this. Let's find, I misread my notes. Let's find the sum of moments about the y-axis for this system. So I've got a system of forces, a system of weights applied to this quadrant system. Let's find how much moment is actually being applied in the y direction about the y-axis. So if we do that, we say, well, your sum of moments about the y, you're going to have, what are the things causing the moments about the y-axis? Well, I've got this z-direction force, all these z-direction forces, and it's an x distance away from the y-axis. So weight 1 is out here at x1 distance. Weight 1 is out here at x1 distance from the y-axis. So that's going to be its lever arm about the y-axis, and that's appearing to apply a positive moment in that y-axis. So I've got weight 1 at x1. And then I've got weight 2, and its lever arm about the y-axis is going to be x2. And then weight 3 is going to have an x3 lever arm. And I could keep adding force weight number 4, weight number 5, weight number 6, and all of them would apply a moment in the y direction based on its weight and its distance from that y-axis. Okay. Now, if that's what I've got, here's what we could do is we could say, well, you know what? This is the product of all of these weights multiplied by their respective x distance. What if there was a resultant weight, a total weight, and I could apply that resultant weight at some specified location, some specified x location, we'll call that x bar. That would be the x location of the center of gravity. That would be the point where I would apply all of the weight. If I combined all this weight to a single force, a single weight, a resultant weight, the x location of it would be this x bar. And where I combine the moments caused by each of these about the y-axis, I could find its x location for that resultant weight. Right? So how would I find that resultant weight? Well, that's simple. I just add up all the weights. That would be weight 1, right? So all the weights, each individual weight from I equal to, n to infinity, essentially, or so, however, whatever the notation is appropriate there. So W1 plus W2 plus W3 plus et cetera, as many weights as we have. And that would give you the resultant weight. And notice what I've got here. Again, what am I trying to find? I'm trying to find this x bar. So if I say, well, where would that be located? Where's the x location for this resultant weight? Well, I would solve for this. So this would be weight 1, x1 plus weight 2, x2 plus weight 3, x3 plus all the things divided by the resultant weight. Well, notice what these are. This is the individual weight multiplied by its individual x value. And this is the individual weight multiplied by its individual x value, et cetera, and that series continues on. So what you have is, in the numerator, I've got this series from I is equal to all real numbers n up to infinity, as many as you have, of whatever the individual weight is times its individual x location, divided by the resultant weight. We've already said, well, the resultant weight is what happens when I add up for all real n up to infinity, for as many as I've got, all the individual weights, the resultant weight. This is how I'd find x bar. Similarly, I could find the y location for all these weights. And the way I would find the y location is I would sum up all of the individual weights multiplied by their individual y location divided by the sum of all the individual weights, or the resultant weight if you like. And the same thing for the z bar. The location, the z location where I would place this center of gravity would be, again, the sum of all of the individual weights times their z location divided by the sum of all of their individual weights. Or again, the sum of individual weights is just the resultant weight. Okay, so that's kind of cool. That would be the center of gravity, G, capital G, would be located at x bar, y bar, z bar. So this would be the center of gravity for a system of individual weights. Well, what if I wanted to find the G, or the center of gravity for a body? So not an individual or a set of individual weights where I would just add them up. What if I wanted to look at some continuous body or some continuous object, some continuous shape, a volume, if you will? Well, lecture 17, page 2 of something. So I don't know, let's just pick an arbitrary shape. And it's not too arbitrary if I say, well, let's just look at a sphere. Right? Let's move this up. So if I look at a sphere and I want to try to find center of mass of this spherical body. X, Y, Z. What could I do? Well, I could break the sphere up into a bunch of little finite elements. And here I would have a differential weight 3. If I've got over here somewhere I've got a differential size slice of weight number 2, and over maybe down here somewhere I've got a differential size slice of weight number 1. Well, I mean, I hope maybe you see some parallels as to what I did earlier. Remember, how did I do this earlier with points? Well, I found each point's X, Y, and Z location and used that to determine, based on these sums, the X bar is the sum of all the individual weights multiplied by their X locations divided by the sum of all the individual weights. Well, what happens if I have a bunch of little tiny differential weights and I add up a bunch of little tiny differentials? What is that? That is an integral. For us as engineers, that's what integrals are. Integrals are what happens when I add up a bunch of little tiny pieces, a bunch of differential size slice pieces. So here I'm going to integrate X with respect to weight and divide it by the integral across the entire weight. And so I would need to know, what does that weight look like? And I'm going to integrate X throughout that entire weight. And then, so I would need to be able to describe this as some function of X to be able to perform that. Same thing here. I would integrate Y with respect to weight divided by essentially the total weight. The integral of dw is just going to be w. That's just going to be the total weight. And the same thing with z. Again, all I'm doing is I'm doing the same thing I did previously. It's just I'm taking each one of these differential weights multiplied by their x or their y location. I'm adding all of those up, and I'm doing on smaller and smaller differential size cubes using a function to do so. So I'm going to have some function to be able to integrate here to make this actually work. Same thing with z. Integral z dw divided by integral dw. Okay, that's nice theory, and again, the centroid or the center of mass for this thing, where I could apply the resultant weight. Well, that resultant weight, of course, would be the integral of dw. And g, again, would be the x bar, y bar, and z bar location of that centroid, or the center of gravity, I should say. Haven't talked about centroids yet. So you can do it if I can describe this as a mathematical function that I can integrate. Well, I just take that function, multiply by x, y, or z, and perform the integral, and we're off to the races. Now, so we'll see that. We won't do a ton of calculus here, but I need you to be able to do the calculus when it does show up. I think we talk about that in the syllabus. Right? Okay. Now there's some other terms. I've already started to throw them around here. Center of gravity and center of mass are interchangeable if density, no, I should say this, not density yet, if gravity is constant throughout the body. Steve, wait, gravity is always constant. Well, there is a gravitational constant, but our gravitational force is reasonably constant unless you get a long distance away from the center of the Earth or closer to the center of the Earth. The total gravity, your total weight ends up being proportional to the square of your distance to the center of the Earth. Most of the time, we don't change that enough to notice a change in gravity. But if you actually, if you took a scale out on an airplane, you could actually measure a slight difference in your weight. Obviously, if you got to the International Space Station, your weight decreases significantly because you've gotten far enough away from the Earth. So we can look at this and say, Steve, isn't gravity always constant throughout a body? Well, yeah, it depends on how large the body is. The bodies that we're going to be dealing with here, we're going to be able to interchange center of mass and center of gravity. We're not going to be dealing with planet-sized bodies in what we're doing. So we're going to be dealing with objects reasonably close to the surface of the Earth where the gravity will be constant throughout that object. So we will be able to interchange these two terms. But we should point that out. Hopefully they talked about Newton's law of gravitation or attraction in your physics class, but there is a slight possible difference. But for most everything we're going to do, these are just fine. These are just fine to be interchangeable. Now, another term to introduce here, so that's center of mass and center of gravity. There's also the term of centroid. Centroid is the geometric center of an object. And so if the density of an object is constant, the object is considered what we call uniform. And if the object is uniform, what that means is that the center of gravity, as long as gravity is constant, is interchangeable with the center of mass. Again, anything we're going to deal with here, center of gravity and center of mass are interchangeable. We've already said that. Now, most of the time, the centroid, the actual center, the geometric center of a shape, most of the time, the centroid is going to be interchangeable with the center of mass. As long as gravity is constant, that's going to be interchangeable with the center of gravity. So for our purposes, these three terms are interchangeable. Most likely, we're talking about the same point, G, within an object. Now, you can have an odd density object. I have, sitting on my desk, or in a cabinet somewhere, this random bar that is, you can see it's obviously two metals that they've joined together, right? And so if you have this bar, again, I could pass it around in class, and I should have grabbed it and brought it home tonight. It appears to be lead on one side, and I think it's aluminum on the other, and I think they're just glued together. And so your center of mass ends up being much more in the lead side because the lead is substantially more dense than the aluminum is. So, but this is a situation where the density is not constant. This is not considered a uniform object because I've got two different metals, two different materials, two different densities. So the center, in this case, the centroid might be right here where the two are joined, but the center of mass and the center of gravity is offset a little bit. And it's an intentional kind of comical example of that, but it's a nice classroom demonstration to pass around, and you can actually feel the difference. If you're on campus, you want to stop by and say, hey, show me the off-centered bar, I'll be happy to show you. All right, I'm going to stop this video there and start uploading it. We'll work on the next one.